Hello everyone, this is Joanne from Kameka. I am an expert application engineer in the SIMS laboratory of Kameka. I am pleased to introduce 7F Auto to you. What I'm going to talk about today is the detection limit analysis of light elements using 7F Auto instrument, especially carbon in silicon case. As it is well known, dynamic SIMS plays a very important role in measuring impurity concentrations, such as hydrogen, carbon, and oxygen in semiconductor materials. It is thanks to its high sensitivity, ability for depth profiling at high throughput, and of course, good detection limits. So let's see how 7F Auto can provide optimized detection limits for light elements. The first is the continuous primary ion beam bombardment, which allows to reduce contamination. And high density of station primary ion beam can reach high sputtering rates. The next is ultra-high vacuum level in the analysis chamber, under 7×10⁻⁻10 millibar. And we can also use a liquid nitrogen trap for minimizing the background level created by residual gases. The third is fully automated multi-storage chamber, which can contain up to 6 sample holders under vacuum conditions. And besides, in this multi-storage chamber, a baking system is equipped and can be controlled by automated way. This means that we can program a baking sequence for multiple sample holders during the night, for example. So what detection limits we can get for carbon in silicon sample? I will present the result obtained using two different methods. The first data I'm going to show you is obtained by called classical conditions. This analysis has been performed using session primary ions at 15 kiloelectron-volt of impact energy and detecting negative secondary ions. The sample was loaded into the analysis chamber the day before the analysis. Then a pre-sputtering has been running during the night using very high current, about 1 microampere on large raster size, 500 by 500 micrometer. The effect what we can expect with this pre-sputtering is cleaning on the sample surface as well as the immersion lens which is close to the sample surface. For this analysis, the pressure in the analysis chamber has been maintained about 5×10⁻⁻10 millibar and a high sputtering rate about 16 nanometer per second was applied. Using these classical conditions, we obtained about 3E15 atom per cubic centimeter as the best carbon detection limits in silicon. It is shown in this profile. Now we go to the second analysis conditions called RASTER change method. This method is quite powerful for analysis of atmospheric species such as hydrogen, carbon, and oxygen, which can be influenced by undesired background signal due to residual gas contribution. This method allows to separate the net content in the sample, so this is what we want to measure, from the instrumental background contribution. This method is based on analysis using two different raster sizes, R and 2R. Look at this figure. First part of depth profiling will be running with the bigger raster size, so a 2R with a given sputtering rate. Then, at some point, we change, in fact, reduce the raster size to R. As a result of this raster change, the sputter rate becomes 4 times faster than the previous raster size. Remember that the size of the analyzed area remains unchanged during this process. For this analysis, we need to record both atmospheric species, in this case it's carbon, and a matrix species, it's silicon. For carbon, signal intensity has two separate contributions. The first part is instrumental background signal from elements that are adsorbed to the surface. Signal intensity does not vary with the sputter rate increase because the adsorbed carbon is only dependent on the analysis area, which is held constant. The second part is bulk contribution from elements in the analyzed volume of material. Signal intensity is proportional to the sputter rate. In case of silicon, which is matrix signal, as background contribution is negligible, so the signal is simply proportional to the sputter rate. Now we will see how to compute the bulk carbon concentration using raster change method. As this method is based on carbon and silicon signal intensity variation when reducing the raster, the bulk carbon concentration can be computed using a simple equation like it is shown here. What we need to know as a result is C value in a square bracket here, and RSF, so relative sensitivity factor, can be applied as usual, and the difference in carbon intensity corresponding to the two raster sizes is normalized to the difference in silicon intensity corresponding to the two raster sizes also. We have seen the principle of the raster change method so far. Now, let's look at the specific protocol that we tried in Kameka. 5 bulk samples was loaded in the auto storage chamber, and carbon implant in silicon Kameka reference sample was loaded with them. We kept both sample holders in the storage chamber during the night. It means that we did not perform a long overnight pre-sputtering. The beam condition was the same as classical method, using session primary ions at 15 kiloelectron-volt of impact energy and detecting negative secondary ions, of course, both carbon and silicon ions. We started analysis about 1 hour after holder introduction in the analysis chamber. During the analysis, the vacuum in the chamber was maintaining about 3 × 10⁻⁻10 millibar, which is not so different from classical method. In the depth profile recipe, we included a short pre-sputtering during 1 minute with 125 micrometer of raster size, which is a bit larger than the first raster size, so 2R. As soon as this brief pre-sputtering is over, depth profile acquisition begins. For the first 15 minutes, the analysis was run on 100 micrometer raster size, and about 15 minutes, we changed the raster size to 50 micrometer. And under this condition, the analysis proceeded for an additional 15 minutes. Thus, the total analysis time took about 30 minutes. Now, let's have a look at the result of this test. 3 depth profiling analyses were performed for each sample, so we have obtained 15 profiles in total. Let's call it one data set. The result is shown in figure 1. We can clearly see a different level of carbon concentration among samples. The data table shows a very good reproducibility for each sample. This test was repeated twice with a 4 weeks interval between two datasets. Similar protocols and recipes were applied, and a similar RSF was obtained. As we see in Figure 2, an excellent agreement is obtained between two datasets. This slide shows two depth profiles measured on both sample number 5 and the sample number 2. These two samples correspond to the highest and the lowest carbon concentration cases. As explained before, the raster size was changed 15 minutes after the analysis started. Comparing these two profiles, we can see the jumping step of silicon signal is almost the same on both cases. On the other hand, carbon profiles are a bit different. While we have a big jumping step of carbon signal on sample number 5, there is a very small step on the sample number 2, which is expected to be the purest one among samples. And this profile confirms our assumption. If we consider to be able to measure the minimum intensity jumping step about 3 counts per second with confidence, by theoretical calculations, this means that we can measure a carbon bulk concentration down to 1e14 atom per cubic centimeter level. Please remind that the sufficiently pure sample is required to realize this test. Summarizing what has been discussed so far, the raster change method provides bulk carbon concentration without background contribution. It is based on carbon and silicon signal intensity variation when reducing the raster. In other words, it can be said that the smaller the carbon intensity increase, the lower the carbon bulk concentration. Excellent agreement between two independent data sets even with a 4 weeks interval between sessions. This demonstrates the robustness of this method and the stability of the instrument. Theoretical calculations show that we could measure a carbon bulk concentration down to 1e14 atom per cubic centimeter. In order to measure this level, a sufficiently pure sample is required. As you have seen so far, the bulk concentration of light elements can be measured in a simple and powerful method, and it can also be applied to implanted samples. This is all we prepared about the detection limit optimization of carbon in silicon. Thank you very much for your attention. Thank you.